Let me share the slides. Attendance. You don't have to worry about attendance because I can just extract your login history on WebEx along with the duration of your login for every single class. So you don't have to do anything. Yep. All right. That's good. Is everyone already in the WhatsApp group, or some of you are still not in the group? Just in case. So I believe everyone is already in the group, yeah? If not, please highlight, and maybe Faris. Oh, Faris is not around today. Maybe somebody from the group can help later on. Okay, so as usual, before I continue, yeah, Amiro maybe can help if there's still somebody or some of you are still not in the WhatsApp group, just in case. So before I continue my class, usually I'll recap on what we have learned before. So let's recap on the content that we've gone through yesterday. Okay. So yesterday we have learned about primary type of material, right? Primary types of materials. And so how many are they? How many types of material did we learn yesterday? 3, right? 3, okay. Okay, can you name them? All the 3? Before we move on. You can unmute yourself, you can write down if you want. So what are the 3? Insulator, semiconductor, and conductor. Okay, good. So what is the difference between insulator, conductor, and semiconductor? What is the obvious difference? Right? The fundamental is in the energy gap. So what do you see in terms of the most obvious property of these 3? Capacity to carry charge, yes. Range of resistivity, or in other words, range of conductivity, right? Yes, conductivity, which is the inverse of resistivity. Okay. So what is the underlying physics behind the electrical conductivity? The band gap, isn't it? Band gap, size of the energy gap. So what makes the metal conducts easily? What makes the metal conducts easily? Why does it readily conduct? Close band gap. Okay, that's close. What's the more accurate word to say? Band gap overlap. Yes, the word is overlap. Okay, so you shouldn't miss that. Overlap of band gaps. So you need to say that the overlap of valence band and conduction band, and this causes the carriers to be there already, so to be around the conduction band edge and ready for conduction. So how about insulator then? How about insulator? Why is it so difficult for insulator to conduct? So anyone? Yeah, band gap is so large. Yes, band gap is huge. So what's the order of the band gap for insulator? For example, just give an example. How big is the band gap in terms of the electron volts? So that we can appreciate the the magnitude of the band gap. Yep, 10 electron volts. If you talk about diamond, then 5.5. So that's the range, okay? So how about the semiconductor then? How about the conductivity of semiconductor? What can you say about conductivity of semiconductor? If you are asked to summarize in like 10 seconds, what would you say about conductivity of a semiconductor material? Anyone? Just in simple terms, simple sentence, what would you say? Conductivity of a semiconductor. How would you summarize the conductivity of a semiconductor in comparison to insulator and conductor? How would you summarize that, say, in 10 seconds? What would you say the conductivity of a semiconductor? Okay, go ahead. Yep, go ahead. Who's that?
Raja Saleh.
Okay, yeah, go ahead.
Yeah, the pure semiconductor is in between the insulator and conductors.
Okay.
So, yeah, and then we need heat or extra efforts to be more conductive, to increase the conductivity.
Okay, that's good. Okay, well, why do you think that is in between? Why do you think it is in between conductor and insulator?
Because of the band gap is small,
Okay.
it's not used as the insulator, and it's not overlap as the conductor.
Yes, that's good. So it's in between, right? So the electrical conductivity is in between because you can also say that the band gap is in between. So it's not too small, it's not too big either. So you need external factors such as doping, heat, or illumination or bias in order to alter the conductivity of a semiconductor material. So you can actually play around with the conductivity level according to what do you want to get, right? So some people say here in between can be as insulator, can also be conductor. Yes, depends on the factors that we introduce to the semiconductor. So in between, you say here, insulator and conductor, it can be configured by doping to make a conductor as per our liking. Yeah, exactly. Good. All right. So now let's move on. So you've got the basic already. Before that, another 2-3 set of questions. How about the crystallinity of a semiconductor? How would you define crystallinity? What is crystallinity? Anyone? You can unmute yourself. You can write it down. So the goal here is to make sure that you have, you can explain to yourself and you can explain to others your understanding of the previous topic. So it doesn't have to be the exact words, but at least if you can manage to explain to yourself, then that means you understand the topic. Yes, crystallinity. So what is crystallinity?
Doctor, repeating patterns
Yep.
of
Yep.
repeating patterns of atom positions in any
Okay. Repeating patterns of atom position. Okay. All right. Anything else?
and
What do I call you? Mushfiquz Zaman?
yeah, Mushfiq, doctor.
Mushfiq. Okay. Where are you from?
I'm from Bangladesh, doctor.
Okay. Right. Then Mushfiq. Okay. All right. That's good. So any other answers? How about Alia here? Alia Nasrin? Order of arrangement of particles. Well, they're not particles per se. They're atoms. Okay, atoms. Okay, Juara. Yep, degree of structural order of solid. Yep, if you look into the slide, then yep, degree of structural order of solid, or the repeating patterns of the repeating arrangement of the patterns of the atoms. Okay, so how many types of crystallinity do we have? The most obvious ones. 3. Okay, name the 3. We discussed quite a lot yesterday on the 3. Can you name the three?
Dr. Amorphous, polycrystalline, and monocrystalline.
Yeah, okay, amorphous, polycrystalline, and monocrystalline, right? So poly can also be said as multicrystalline depending on the context. But generally, let's just say amorphous, poly, and mono, right? So now let's move on to impurity and doping. Okay, impurity and doping. So when we talk about impurity and doping, we are talking about addition of foreign atoms into host lattice. So when we talk about host lattice here, I'm always referring to silicon because silicon is the what I call the benchmark for the technology now. You can also refer to some other semiconductor material, of course, but to simplify things, let's just assume silicon is the host, and relative to silicon, then we can discuss all the impurities, either they are desired or undesired. Okay, so if you look at the periodic table here, in group 14, silicon is here. So some also say group 4 with 4 valence electrons. Okay, so we want to see what are the effects of impurities, foreign atoms, dopants, depending on the context, to the silicon as a semiconductor material and eventually as a device. So when we say impurities, we can generally divide impurities into two types. So the first one is undesired impurities, something that you don't want to be in the lattice. And the second one is desired impurities, something that you want to be in the lattice, okay? Undesired and desired. So if you look at undesired impurities, so they are generally, well, it's not always applicable to all cases depending on the context. But generally, if you talk about semiconductor physics, metals are undesired impurities. So examples are gold, copper, nickel, iron, sodium, and others, okay? Generally, they are undesired impurities, so you don't want them to be in the silicon lattice. So if you talk about carbon and oxygen, for example, you can say that these are an exception, if you like, because small amount of controlled oxygen can help gather. Gather means they can gather or collect. They can be as a sink, a place for the contaminants to sink and be removed eventually. So this is more related to the process later on. You're going to learn in 47 if you take semiconductor fabrication. So we're gonna need some amount of oxygen to up to some level in order to enable gathering process. So the word here is gathering process. So gather or gathering process. Gathering basically means collecting unwanted impurities from the active area of your device and then isolate them into inactive areas. And then in the next process, in the fabrication, you're going to remove the inactive areas out of the device. Okay, so you collect the unwanted impurities first, and then by the next process, which is usually wet chemical, you will remove the collected impurities out of the device, out of the material. So that's gathering. Okay, so they are the undesired impurities. They are generally detrimental to the devices, so they are bad or severe to the devices. Okay, so extremely low impurity concentration. Well, this one depends on the requirement of the device. There's no one specific answer for this. It depends on what sort of device are you working on. So if you're talking about integrated circuit, then they are very, very sensitive. So if you're talking about LEDs, lasers, they are very sensitive as well. If you're talking about solar cells, for example, they are rather robust. So in that sense, they are more tolerable to defects or impurity, if you like. Okay, so there's no one answer. It really depends on the device that you want to use. So if you talk about integrated circuit that we have in our phone, laptop, iPad or something, or some other electronic gadgets, then we're talking about using semiconductor grade silicon. Semiconductor grade silicon, let me write it down here on the screen. So semiconductor grade means you cannot simply use any grade of silicon in order to fabricate the chip. So you need to have certain level of purity in order for the chip to work. Okay. So if you talk about purity of the semiconductor material to fabricate semiconductor device, so in this case, if you talk about integrated circuits or basically transistors that you have in our phones and others, so we are talking about 9N of purity. 9N of purity. So what is this 9N? What does it mean? So it means your silicon, to be able to work as an integrated circuit in your device, so it has to be of what, 99.1234567% pure. So if you count this, you're going to get 9N. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9N. So that's what it means by 9N. So you need to have 9 of 9s, right? Purity level in order for it to work as a semiconductor, as an integrated circuit in our devices. Okay, if you have 8N or 7N or 6N or 5N, they're not going to work as your IC. So that's why I think in the first class, if I'm not mistaken, I did explain about to be able to get the sand as the raw source, as the raw material. So you need to use silicon to be fabricated as a device eventually, and that silicon wafer has to have 9N of purity. So to be able to reach 9N from the sand, so what you have to do is you have to firstly reduce the oxygen or remove the oxygen from the silicon dioxide, which is sand, to be able to get silicon, and then you have to go through a couple of purification steps in order to purify the silicon up to the 9N level. Then only the wafer will be ready for fabrication. Okay, this is going to be learned in detail in 487 next semester. So on the other hand, to put things into perspective, if you want to use your silicon for solar cell, for example, okay, solar cell just now was IC, now solar cell, you only need 6N, just 6N, so 6 of 9s. So let me just admit your friend here. Okay, 6N, so that means you need 6 number of 9s, 99.9999, for it to be a good solar cell. So you don't have to go for 9N silicon in order to fabricate solar cell. And this is really significant when you talk about the economic of the process, because spending money for 9N will be a lot more expensive than spending money for 6N. So 6N is obviously cheaper because you don't have to go for a very high level of purity in order to realize your devices. On the other hand, if you use the 6N for IC, it just wouldn't work. Okay, so that's a requirement of the industry that you have to understand. So now it goes back to the impurities of the impurities that we need in our semiconductor material. So 9N, so it has to be pure. It has to be usually, if you look at the specifications of your wafer for certain industry, silicon wafer for IC, for example, or silicon wafer for solar industry, there'll be a range of specifications that have to be fulfilled in order for the wafer to work successfully. So now, if we talk about doping, just now we talk about impurities undesired, which in which we don't want them to be in lattice. The other part, the second part, is called desired impurities. So when you talk about doping, you want to incorporate foreign atoms into the lattice. You want to do it purposely, right? So the first one is now you want to avoid at all costs. Okay, the first one here, undesired, you want to avoid them at all costs. And the second one, you purposely want to incorporate them into the lattice. Okay, so, and these desired impurities, if you talk about this doping, these desired impurities, doping is desired impurities, right? Incorporating desired impurities into the silicon lattice. So now let's explore what is doping. So let's discuss again. So let's get started. You can go on Google search or something and we discuss here. So let's get started with the first one. What is doping? Can anyone give me the definition of doping? You can go and search for a couple seconds and share here. So what is doping? How do you define doping? Doping for semiconductor, okay, because doping generally is something else as well. But this one is doping for semiconductor. Anyone?
Doctor, introduction of foreign objects into a system.
Okay, introduction of foreign atoms. Okay, continue.
Yeah, which enhances the performance of that material or something.
Yeah. Okay. So you introduce or incorporate foreign atoms, foreign materials into the silicon lattice in order to improve performance of the material. Amirul, you on mic, yeah? Amirul? Wi-Fi dah okay ke Amirul? All right, add something into pure product. Yep, add something to pure product is general. Yep, you introduce foreign atoms into silicon lattice or semiconductor lattice in this case. So, okay, so that's basically what it is. So why do we do that? Why do we dope? Okay, you said, Shreyas said, adding impurities to a pure semiconductor to increase number of charge carriers. Okay, Shreyas, why would you want to increase the number of charge carriers? Yeah, go ahead, unmute yourself. Why would you want to do that? Why would you want to increase the number of charge carriers? Shreya, would you like to explain on that? Elaborate? Or somebody else? So why do we dope?
Doctor, in the case of semiconductors, we dope in both ways to create holes and to create extra charges, right? So that we can actually increase the amount of charge carriers down there, so that it can actually jump off the band gap and also lower the band gap.
Okay, we want to increase the amount of charge carriers, electrons or holes into the silicon lattice. So we have more carriers available. So end of the day, what do you want to achieve? So some of you have said here, Derwina, Juaria, Fatin, to increase conductivity, right? To increase conductivity. That's the end of our goal. If you go back here, if you go back to the chart that we discussed, yeah, if you go back to this chart, we have discussed about the spectrum of conductivity or resistivity, if you like, of your semiconductor to the left or to the right, to the lower resistivity or to the higher resistivity, or on the other hand, to the higher conductivity or to the lower conductivity. So the goal of our doping process, the introduction of the foreign atoms into the silicon lattice, is to modify the electrical conductivity. So that's the goal. Modify electrical conductivity. Okay, so you can make it more positive, you can also make it more negative, right? So by adding specific charge carriers into the system or into the silicon lattice, so you can actually add more holes. So if you add more holes, what do you call that? Are you making it more positive or more negative? Are you making the silicon more positive? Yeah, more holes, p-type, more positive. Okay. So on the other hand, if you're adding more electrons, so negatively charged naturally, if you're adding more electrons, you're adding more negative component into the system. So the silicon is getting more and more negative, hence it'll be more negatively charged. Right, that's good. Next one, how do we do doping? How to do doping? Even though it's more on the process itself, but let's just have some ideas of how do we actually do that. Okay, increase temperature. Okay, go ahead, Mushfiq.
Doctor, we may take a very pure like 9N silicon wafer, then we just take it to various chemical processes where we introduce like galliums and stuffs to introduce more and more holes or carriers.
Okay, so if we talk about how to do doping, you can actually divide into two. So we have discussed about more holes or more electrons. Okay, the first one is more holes and the second one is more electrons. So you can either go for the top one or the bottom one. So you need to be clear in the first place. You have to come here, go back to the periodic table. Remember that your silicon is the host atom. Okay, so if you want to do, if you have to have more holes into the system, you need to use group 13 as your dopant. Okay, group 13 as your dopant. So it will introduce more holes to the system. Why? So let's see later on. So if you want, on the other hand, if you want to make it more negative, if you want to introduce more electrons, you have to go for group 15. So you may use phosphorus, arsenic, or antimony, adding them into the system at control level in order to get your desired resistivity or conductivity. Okay, so increased temperature, yes. So for example, if you talk about holes, then typically in the industry we use boron. Okay, remember this one is group 13, yeah, group 13. Below here is group 15. So you can use boron and gallium. These are the two common ones. Okay, so these are the two common ones. On the other hand, if you want to introduce more and more electrons into the silicon lattice, in the industry we normally use phosphorus or arsenic or antimony. These are among the common ones, but phosphorus is the most common of these three, and boron is the most common of these two. Okay, so let's see how it actually works. How do you actually get more holes and more electrons? So what is the end result? The final question here, what is the end result of your doping process? What do you expect?
Doctor, a lower band gap and narrower band gap.
Narrow band gap, yes, narrow band gap up to some level. So it won't happen at low level, but it will take place at high level of doping. We're gonna see later on. So what else is the expected result? So go back to your objective. What are you trying to do with doping?
To make it more conductive, to
make it more conductive, right? To alter conductivity. So your end result is your conductivity is increased or is altered, or you can even counter the charge, positive to intrinsic to negative. You can do you can go many ways, right? So end of the day, you manage to alter the conductivity of your semiconductor material as desired, right? So let's go. So let's go through the content now. So good, you've got some basics already. So now let's go through desired impurities, which is related to doping. So primary technology that enable formation of multiple solid state devices on the same substrate. So this is incorporation of the foreign atoms. So you can define the process as incorporation of the foreign atoms into a host lattice. So in this case, we're talking about silicon as a host lattice. Then we are referring to group 13 for p-type and group 15 to make it more n-type. So it's going to give you significant effects on the electrical properties of the silicon, since the goal of doping is to alter conductivity, or to be more specific, most of the time is to improve conductivity, right? But you can also go on the opposite side. You can also reduce the conductivity of the material by adding unwanted impurities. So that's a bit tricky, but it can be done as well. But the most straightforward content here is to improve conductivity, right? So you need to add a very small percentage of the dopant from group 3 or 13 for p-type or 15 for n-type into the silicon in order to improve the conductivity of the silicon. So normally, is there any of you working on silicon wafer in the FYP now? Anyone working on silicon wafer? Handling the silicon wafer, do the measurement, do deposition and stuff. Do you get to work with silicon wafer? in our lab? Anyone? Not yet, maybe? Or your title is more on the silicon wafer? No idea yet. Okay, it's okay. Anyway, if you work on silicon wafers in our lab, all right, not you, okay. If you work with silicon wafers in our lab, you will normally be given a batch of silicon wafers, a pack of 25 wafers usually, and the wafer that we have in our lab is 2-inch. The common one is 2-inch, the diameter, okay, round shape. So normally, in order for you to pick, you need to know what is the resistivity of the wafer that you need. Okay, so you won't be able to see the doping level if you look at this chart. So this chart shows to you a resistivity of the wafer of the silicon on the y-axis. So this is the resistivity or the inverse of conductivity, and the x-axis is the doping level. Okay, Na or Nd. Na refers to p-type because that is the N is for doping level or doping concentration, if you like. For acceptor, we want to see that why is it A? So it's for p-type. To make it more p-type, then you have to use Na as your reference. On the other hand, if you want to make your silicon more negatively charged or more with more of electrons, you will make it n-type, or you refer that as Nd. Concentration of donor atoms, acceptor atom. We're going to see later on. Acceptor here means A means your dopant is coming from group 13, like boron or gallium, for example. And the dopant atom, a donor, sorry, not dopant. Donor is group 5 or group 15, like phosphorus or arsenic or antimony and stuff. Okay, when you pick the wafer for you to start your experiment, you don't go and pick the doping level. You will not be given the value. So you will be exposed instead to the resistivity of the wafer. So when you get to see the wafer pack, it's labeled with the resistivity range of the wafer. So for example, if the wafer pack states that the wafer has 1 ohm cm, so if it states 1 ohm cm of resistivity on the pack, and you need to know then the second parameter, whether the wafer is p-type or n-type. Okay, this is dope wafers, right? These dope wafers, not intrinsic, not pure. So dope already. So what you have to do then is you can always come back to this chart, this curve. Check out here 1 ohm cm. So be sure whether your wafer is n-type or p-type. If your wafer is n-type, so that means you just can come down here, more or less. So that means your doping level in the silicon wafer is somewhere 5E15, more or less. 5E15, or 5 times 10 to the 15 centimeter cube minus 3, minus cube, right? Or per centimeter cube. So that is the doping level that you have, the doping level of the electrons, because it's n-type, right? So to relate to our previous pages, of electrons, 5E15 of electrons in the silicon wafer has been doped into the silicon to improve its n-type conductivity. On the other hand, if you look at the pack states that you are dealing with p-type, and you need to go to the right a little bit here, and then you can come down here. No, sorry. So it's somewhere 1.5 E16. So 1.5 E16 per centimeter cube of holes already doped into the silicon. So that is that's the doping level that you have in the silicon. So you are not exposed to the value of the doping, but instead you're exposed to the value of the resistivity. But you can always go back to this curve and check out what's doping level like in the wafer. Okay. So this doping level may range from, in the semiconductor industry, it may be from 1014, for example, down to 1014. You may use a dope wafer down from this level, 1014. It can be up to 519 usually. So you can also deal with intrinsic wafer where the silicon is undoped, and in that case, if it's intrinsic undoped, intrinsic is usually about 10 to the 10. So that means if you see 10 to the 10, that means intrinsic or pure. It's not doped. So as long as you see it's 10, 14 and above, it's dope already. So you just have to check out whether it's p-type or n-type, and come back to this resistivity concentration curve. So how do we get p-type? Okay, so we've discussed a little bit just now, p-type and n-type. So now let's go to p-type, which makes the wafer more positively charged because of the presence of holes as the majority carriers. So remember this, majority carriers, because later on in the course you're going to learn about majority and minority carriers. So in this case, it's the majority carriers. So the hole is the majority carriers. Okay, so hole is the majority in p-type wafer. So look at the bonding of the silicon here. The silicon is bonded to another 4 neighboring atoms. Okay, so that's the original silicon. If you don't dope the silicon, so you're just gonna see silicon. You're just gonna see silicon here. There's no boron at all. But the moment you incorporate boron atoms into the lattice like this, so you see B here, B here, B here, and boron is from group 13, right, or group 3. So in the covalent bond, it lacks 1 valence electrons because it's from group 3. So the valence electrons for boron is only 3, and the valence electrons for for silicon is 4. So boron lacks 1 valence electrons. Okay, so holes are the primary current carrier. Boron is p-type dopant because it's coming from group 3. Dopant atoms are referred to as acceptor because it has one short of electron, short of 1 electron. So we call it acceptor because it is short of 1 electron. On the other hand, later on we're going to see if we dope using n-type. So n-type has 5 valence electrons and silicon has 4. Therefore, your dopant has 1 excess electrons. So that's why it can donate to silicon or donate to the lattice for the conductivity improvement. So therefore, we call it ND, donor. For this case, for p-type, we call it NA or acceptor. So that's why on the curve is now on the previous page, we refer this to as Na, acceptor, because it's short of 1 outer electron. So acceptors have a vacancy or hole that readily accept electron from neighboring atom. Okay, this vacancy can migrate under the influence of electric field, and even though you can just leave it in equilibrium and it will still wander around. Okay, so that's for p-type, where you use boron with 3 valence electrons in order to produce hole here, right? So due to the 1 short of electron or the absence of electron, we learned before in solid state physics, absence of electron is called hole, right? So absence of electron is called hole. Hole is absence of electrons. Absence of electron. So since it lacks 1 electron, so you have 1 hole, right? So that's what it implies. On the other hand, if you dope your silicon with n-type, or you incorporate foreign atoms from group 5 or group 15, which has 1 excess electron, right? Because group 5 has 1 excess electron in the bond, and silicon has 4, so therefore 1 electron is free to wander around the lattice for conduction. So electrons are primary current carriers. In this case, electron is the majority carrier. So on p-type, in p-type, hole is the majority carrier and electron is the minority carrier. So on the other hand, if you talk about n-type, electron is the majority carrier and hole, as the opposite, is the minority carrier. So we're going to learn about majority and minority later on, and we even have to do calculations on the majority and minority carriers. So dopant atoms are referred to as donors because it has 1 extra electrons in the valence band. So this 1 excess electron is free to wander around the lattice. Okay, so that's how you get p-type and n-type silicon. So typically for application in semiconductor devices, you can you can either use p-type, or you can either use n-type, or you may combine in some situations, or in most situations. And in some cases, you may also have intrinsic as well, referred to as I. So some even have PIN, right? So later on, we're going to learn about how do we apply the use of p-type material combined with n-type material together to form a junction. And this is a PN junction, right? This is where, for example, if you talk about here p-type silicon, p silicon combined with n silicon. So that means you need to combine your boron doped silicon on the left hand side with phosphorus doped silicon on the right hand side together to form a junction and to eventually make a device. So we know that device like what's lasers, solar cells, LEDs, detectors are based on PN junction, right? They are not only limited to PN junction, they even use architecture of PIN junction. So that means in this case, we have a thin intrinsic layer in between PIN. You have a P and you have a very thin intrinsic layer, undoped. Okay, remember intrinsic is undoped, and then you have N together. So the intrinsic in this case is sandwiched between P and N. So you're gonna have PIN junction. So you may use PN junction or PIN junction. Okay. And if you talk about the PN junction, for example, we're gonna come to this later on in more detail. But this is just an introduction, though. The level of doping in P and N may vary according to your needs. So your P may be, I don't know, 1014. It could also be 1016. It can also be 1018. It can also be 19. And on the other hand, this guy can go 14 as well, 16, same. So you can combine P and N of 16 and 14, 18, 16, 16, 16, 18, 18, 19, 19, 17, 17, or undoped even, well, depending on what you need to use. So if you talk about solar cell, usually if you talk about silicon wafer, then the bulk of the solar cell uses doping level of 1016, and a very thin layer forming the junction on the top of the solar cell typically uses 1019. Okay, so the doping range really depends on the device that you want to use. Yeah, that's done for today. So that's basically the basic of doping. So do you have any questions? Anything on the doping or impurities that you're not sure of or you don't understand? We'll come back in more detail later on as we go through, you know, recombination, the effects on the device and stuff like that. But this is just an introduction of what are undesired impurities, like metals generally, and on the other hand, desired impurities, which are generally dopants, the atoms that you want to incorporate into the silicon lattice in order to alter the conductivity, and then the basic of doping itself, right? So maybe I can add like 1 or 2 more minutes. In order for you to do the doping, we can do by multiple processes. Anyone working on doping in your FYP? Anyone working on a junction, PN junction? Okay, Rafai. What are 10, 14, 10, 16? Okay, right. 10, 14, 10, 16, 10, 10, 10, 18, 10, 17, 19 is the doping level, right? The doping level. So if you want to relate this to the end result, you can also say that, so as a result, your doping level or doping concentration or carrier concentration is referring to the same thing, okay? Doping level or doping concentration or carrier concentration as a result of the doping process can be in the range of 10, 16, for example, per centimeter cube. So, or you can also have like 3 times 10 to the 17, maybe, per centimeter cube. This is the doping level that you're talking about after the process, or even before the process, if you're working with an already doped silicon wafer. So it's doping level, yeah, okay? So any other questions? So for example, let me just add a few more minutes. You can use in the process, if you want to incorporate boron, for example, it can be in the form of gas, B2H6 gas. Okay, we normally do the process by using gas as our precursor in order to incorporate our dopants. So this is the common one, right? B2H6 gas or diborane, called diborane, D-I-B-O-R-A-N-E. Let me just write it down in the chat box. Diborane, right? So that diborane is B2H6, okay? B2H6 gas. So it's something that you use in the process to do the doping process. So on the other hand, if we talk about phosphorus, you can use phosphine. Phosphine. pH3 from a second. pH3, 3, yeah? And then you can also use POCl, POCl3. Don't worry yet, this is just an idea for you, okay? Because if you get to learn on the process later on, the fabrication, we'll go through the actual gas, the flow rate, and how much of the gas, and what's the effect, and stuff like that on the device. All right, Hifzan, is the doping level the same as the number of atoms in the material? Yes, you can say so, but there's a but to that. Okay, what you put into the lattice is what you want to get. Okay, if you put 10 to the 18, for example, 1 times 10 to the 18 of atoms into the lattice, so you want to get exactly 1 times 10 to the 18 per centimeter cube as well. But, so there's always a but, it depends on the ionization efficiency during the doping process. So I haven't covered this one yet. Ionization process. So if you put 1018 into the lattice and then you want to get 1018, so that means you need to get 100% ionization of the dopants in the lattice. So that means whatever you put into the lattice, they are then electrically active, right? So they can ionize, they will ionize and they will be electrically active. Electrically active. So can there be any not electrically active dopants? Yes, the answer is yes. So you may get some portion of your dopant atoms which may not be eventually electrically active, and in that case the ionization is not 100%. So it may be 90%, 92%, 99%, you wouldn't know for sure. But usually what you get, the carrier concentration as a result of doping, is pretty close to what you put into the system during the process. But for simplicity, we assume that all the dopants are 100% ionized, okay, unless otherwise stated. If it's stated that only 90% of the dopants are ionized, then if you put 1 times 10 times to the 18, then you have to multiply with 0.9, which will make it 9 times 10 to the 17 per centimeter cube that are active electrically for conduction. Okay, good question, right? But normally in the questions, if it's not mentioned about ionization or electrically active dopants, you can safely assume that 100% is ionized. If it's stated, then you have to include 0.9 times the actual concentration in order to get the actual actual carrier concentration active to do the conduction. Right, any more question? Good, yeah, all right, that's good. Okay, so no more, yeah? Okay then, so I'll see you tomorrow 10 a.m. for the new topic. So I'll upload the slides later on today for the topic tomorrow. Okay? Okay then, I'll see you. Bye-bye. Take care. Stay safe. Assalamualaikum. Yeah, welcome all. Bye.